Don't have that many people, but again, it is optional, so no big deal. Go ahead and chat me your first and that last name so I have you for attendance if you haven't done so already. I want to let you know, guys, know first off, I'm very sorry about having to miss so much this week. We had the snow problems, and that forced us to actually do everything remotely on Monday, and then Tuesday I ended up getting deathly ill. Not literally deathly. I just felt really, really horrible. I haven't been that sick in a long, long, long time, maybe 20 years or so, but it was bad. Uh, so I sent out video links and suggestions of videos to watch, and that was supposed to be in lieu of lecture. So hopefully you guys have watched those. I did, of course, cover chapter 19. There was one example I didn't get to cover, and I wanted to make sure you guys had seen one like it, so that was one of the links I sent you. We're going into chapter 20 now, but it's a shortened version of chapter 20. In fact, when I first started teaching at TCC, we never even covered chapter 20, but I just don't feel right about covering thermodynamics without doing anything with the second law of thermodynamics. So what I've done is sort of a abbreviated version of chapter 20 where I get through sort of the bare necessities and talk about what's absolutely essential. The main thing I want to tell you guys about this chapter 20 that you definitely need to know is there's multiple versions of the second law of thermodynamics, and I want you to be able to recognize all of them. So I would take the time to go through your chapter and write down every version of the second law of thermodynamics verbatim and just not so much memorize it where I'm going to ask you to restate it word for word, but you should be able to, for instance, pick them out of a multiple choice where they're actually stated. Not only pick them out, but tell which one's which one's the Kelvin-Planck statement, which one's the Clausius statement, which one's the general statement, which one's the equivalent of the general statement, that sort of thing, which one's the Carnot theorem. Uh, Additionally, as I'd been telling you before, is anything that's called a law or anything that has a whole chapter named after it, you should probably commit that to memory, and at least in your physics classes. But I'd recommend that in your physics, math, and chemistry classes as well. So that means the first law of thermodynamics and the zeroth law of thermodynamics, because you obviously we covered that or talked about that previously. But the zeroth law of thermodynamics, the first law of thermodynamics, the second law of thermodynamics, and your book talks about the third law of thermodynamics. So I want you to have all those written down, sort of memorized. Again, not necessarily being able to state them verbatim, but being able to recognize them from, from made up stuff because I can, put some words together that sort of sounds a little pseudoscientific or at least sounds scientific, even though it's pseudoscientific. So be prepared for that type of question and you'll be much better off. So just make sure you commit all those to memory and not only just for, the test that covers chapter 20, but also for the final exam and for subsequent tests because all of my tests are comprehensive. So I could ask you that question on any test from here on out, a question about, what state the second law of thermodynamics, or check all the versions to the right that are the equivalent of the second law of thermodynamics, so on and so forth. So make sure you guys do that. That's why I'm saying it now on this recording, so you can always go back and look. With that in mind, let's go ahead and get started on chapter 20. But before, does anybody have any questions before we get started? All right. Well, it looks like we're in good spot then, because no one has any questions. I know I just looked in the homeworks for chapter 19, and for some reason, they said they were due like on four, or I think it was like last year or something. But I was almost 100% certain I'd fix that. Well, I have fixed it now. I don't know why it was that date. Obviously, I screwed up and either changed the date but never hit save, or changed the date, hit save, but my computer lost internet connection or something. All I know is the dates weren't right. And I didn't expect chapter 20 dates to be right, but I did expect chapter 19 to be right. So I apologize for that. I've pushed the deadline for chapter 20. I think what I did was, if I remember correctly, I think I made the chapter 19 conceptual questions and chapter 19 part 1. I think I made them due on the 15th, which is basically a week from yesterday. And then I made not the 15th, the 11th. And then I made the part two for chapter 19. I made that due on the 15th, which is Sunday, which technically I should have made it to the Monday. I might even go back and change that, but just keep an eye on that deadline. Don't want you to miss that. And chapter 20 I made due on the same date as part two of chapter 19 because there's going to be a very small part of chapter 20 that's going to be done. I did go through the questions in chapter 20, and none of them are about the other stuff. So, for instance, I'm going to cover the Carnot engine, efficiency of the Carnot engine, entropy to some extent, but I'm not really talking too much about heat pumps and that sort of thing. I like you to learn them and understand it to some extent, so I left the tutorial questions in the homework. So you'll get some learning, but I'm not gonna test you on that. I will only be testing you on whether you know the second law of thermodynamics, whether you know the various versions of the second law of thermodynamics, whether you can calculate the efficiency of a Carnot engine and engines in general, and then some other just generic statements about entropy and stuff of that sort. So let's go ahead and get started by sharing my iPad screen with you guys. Okay, so here we are. Chapter 20, the second law of thermodynamics. I tried to write all these things up so that I could actually have them in front of me and you wouldn't have to refer back and forth to your book so much. I apologize. It's just way, way slower to write in script instead of in cursive, so I wrote everything in cursive. Starting off with the Clausius statement. And the whole reason why we need a second law of thermodynamics before I get into all this is, as I said before, I've mentioned a couple times, the first law of thermodynamics really is a statement of conservation of energy. It basically says that any heat that you put into the system minus any work done by the system is equal to the change in internal energy of the system plus the change in kinetic energy of the system plus the change in potential energy of the system. That's it, showing the entirety of the conservation of energy aspects that the first law of thermodynamics is. But it turns out there's a lot of things that obey the first law of thermodynamics that never happen. And for instance, I use the idea about a coffee cup falling off of a table and hitting the ground and shattering and all that good stuff. And then if you tried to do a calculation with that and you said, okay, imagine the coffee jumps up out of off the floor, lands in the coffee cup while it's assembling, and then the coffee cup lands reassembled back up on top of the table where it started from, that would not violate the first law of thermodynamics, but we know that never, ever, 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 ever happens. So that is one of the reasons we needed something else to explain why do we not have those occurrences, whereas we do have occurrences of the coffee cup falling off. So that's the importance, or one of the important things about the second law of thermodynamics. So I'm going to start off with reading the Clausius statement of the second law of thermodynamics, and it says heat can flow spontaneously from a hot object to a cold object. Heat will not flow spontaneously from a cold object to a hot object. What do we mean by spontaneous? That means without adding extra energy or anything like that. This happens all by itself. And you know it. If you, for instance, lean up against a cold piece of metal, for instance, outside in the snow, like we recently had, if you lean up against, let's say, a Mack truck or something like that, that's ice cold, your bare skin up against it, you will feel how cold it is. And what's going on there is the heat from your body, which is obviously a warmer temperature than the part of the exterior of the Mack truck that you're leaning against, the heat in your body is going to cause the system of the Mack truck's surface to actually increase its temperature. And the reason why is heat is flowing from your body, which is at higher temperature, to the Mack truck surface, which is at lower temperature. You don't find it the other way around. You're never going to find, for instance, you lean up against a cold, ice cold truck, and all of a sudden you get even more hot and the truck gets even colder. That would be spontaneous heat flowing from a cold object to a hot object, and that never happens. So that's the second law of thermodynamics. This version is a little too limited in scope, so that a more general statement is needed. To that end, we must discuss heat engines. So it's going to turn out that we get very different versions of the second law of thermodynamics, and they seem almost completely, distinctly different. But in reality, it turns out we've managed to prove, we meaning physicists greater than me, uh, they've managed to prove that all of these versions of the second law of thermodynamics are exactly equivalent. So it's not too big of a deal for you to worry about that. If you decided to major in physics, you'd go on to learn how these can be equivalent, and in some cases, it's usually shown to you within the first 2 or 3 years of undergraduate program in physics. So, or in thermodynamics and engineering, you often find out as well. So, I first want to tell you what a heat engine is, so you can make some sense of it. A heat engine is any device that can change thermal energy into mechanical work. Remember, thermal energy is just another word we use for heat, and I like to think of heat as sort of a bastardized version of energy, just because once energy is converted to heat, you're never going to get all of that energy back out. That's the version. That's why I call it a bastardized version. It's sort of like it's tainted or something, so that when your energy, which might have been potential energy, it might have been kinetic energy, it might have been ATP or whatever, any of that kind of stuff. Once it's converted to heat, you're never going to get it all back out. And you can imagine on a microscopic level the reason why. And your book follows up on this towards the end of the chapter, where it talks about microstates and macrostates, and that's the ultimate goal of the second law of thermodynamics that I want you to understand. But basically, it would be sort of like you taking all that heat and it's being all that energy and converting it into heat. That means each of the individual molecules in the item that you're studying has now accumulated an extra specific amount of kinetic energy. And because of that, you're going to then try to pull it back out. What's the odds that you could go to 10 to the 25th molecules or atoms and get exactly the right amount of energy out of each of them? From that standpoint, you can see that statistically speaking, it should be low probability. And in fact, that's another version or another way of thinking about the second law of thermodynamics, in which you can reach the same conclusion that heat only flows spontaneously from a cold object to a hot object. And when it does, it sort of loses its oomph because uh, it cannot all be retrieved. Sorry, I was doing multiple window things at the same time. So with that in mind, what we have here is a model of a heat engine. This red part up here is what we call a heat reservoir. You can imagine it like being a big lake. Like, for instance, if you get your body in a lake, and the lake is obviously normally colder than 98.6, what the average human temperature is. So when you get in there, because the lake is so big, such a huge body of water, heat is going to constantly flow from your body into that water. And in fact, if you stay there long enough, you will get hypothermia and bad things that happen. But under no circumstances is that temperature of that lake going to change as a result of that, because the lake is so big. So that's what we do when we think about heat reservoirs, is we imagine just some object that's so big that no matter how much heat you take out of it, you're probably not going to affect its temperature. And that's the same thing that we see down here in the blue. That's a low temperature heat reservoir at temperature T sub L, whereas the red one's a high temperature heat reservoir at temperature T sub H. And the engine is this little green part I have drawn here. But what we see is this heat reservoir has a certain amount of heat, Q sub H, meaning Q from the hot side, entering the heat engine. And some part of that Q sub H is going to do some kind of mechanical work. That's what you see that arrow here. And the rest of it will go as Q sub L, meaning low temperature heat. And that QL is going to go into the low temperature reservoir. So useful heat engines run in a repeating cycle. The system repeatedly returns to the starting point so that the change in internal energy is zero for each cycle. And from this, you can just look at it and you see the total amount of energy coming in is obviously QH, and there's only two ways for it to get out, W and QL. So QH must be equal to QL plus Q plus W. Now, if delta E internal was not zero, then you could have QH minus QL minus W is equal to delta E internal, but delta E internal is zero, so that's how we get this expression. Anybody have any questions on that part? because I didn't write out all of this bit by bit, but I figured you could figure out that QH coming in, W and QL coming out. That means that QH has to equal W plus QL. But also, if you still had some skepticism or skepticality about it, you might remind yourself that delta E internal is Q minus W, and the total Q in this case would be QH minus QL. So, because the QL you're losing and the QH you're adding to it. Any questions on that? All right. So, in order to make the heat engine have anything to do with with the second law of thermodynamics, we have to talk about its efficiency. And in general, efficiency is defined as what you get divided by what you paid for. Now, when I say that, I mean what you get that you really wanted and is useful divided by everything that you put into it. So, it's not just the amount that you put into it that you got out, it's the total amount that went in. So, therefore, we reached the conclusion that the efficiency E is equal to the work put in divided by QH because the total amount that we put in was QH. As you can see from this diagram right here, the total amount in was QH, and the stuff that we got out that was useful was W. That doesn't mean we can't, later figure out some way to make the heat engine a little bit more efficient by grabbing some more of the QL, but then you'd have to redesign a whole nother heat engine and all that good stuff. The main thing is at some point you're going to have to reach a conclusion where, okay, I've got a heat engine right now. It's putting out this much work, it's taking in this much heat, and it's putting out this much heat. I need to take a W over QH and compute the efficiency. Therefore, for a heat engine, we get, notice I've taken the W, which we said QH is equal to W plus QL. So if you solve for W, you get QH minus QL, and that's why we have the expression E equals QH minus QL over QH. We can separate that fraction. That makes QH over QH, which is just 1, minus QL over QH. So the efficiency for the heat engine is 1 minus QL over QH. And that's for all, and that's for all heat engines. We're going to specifically talk about the Carnot engine, but there's also an Otto cycle. You'll see in your book, your author handles the Otto cycle as an exercise. That's an interesting one, and it looks like it might be, somewhat of the origins of the phrase automobile. But it is interesting either way. There's also a Stirling engine, and there's other engines as well that theorists have come up with. And you might even see actual Dodge vehicles riding around with a big word Sterling on the front because that's actually somewhat related to the design of that engine that those particular Dodge trucks use. I've seen them on fire trucks. I've seen them on an ambulance and just a regular, like a 3500 truck as well. So to cement this, let's look at an example. Example: a car engine has an efficiency of 18% and produces 25 times 10 to the third joules of mechanical work each second. How much heat input is required? And I'm not saying this part, but it should be each second. And B, how much heat is discharged as waste each second? So to solve this, what we have to do is use the equations that we know. And the equation that we know is E is equal to work divided by QH, which we just found was in fact equal to 1 minus QL over QH. Now, what we have here is that the efficiency is 18%, so I'm going to say E is equal to 0.18. Notice I had to convert it to a decimal. That's what the efficiency is. If I wanted a percent, I'd have to take this formula and multiply it by 100 with a little percent symbol on the on the side. So that's what we're doing here. And it says it produces 25 times 10 to the third joules of mechanical work. So that's our W. That means we're going to use the W over QH formula instead of the QL minus QH or the QL over QH formula. So I have W is going to be equal to 25 times 10 to the third joules. So now I can plug all this in, and what I get is 0.18 is equal to 25 times 10 to the third joules over Q sub H. And what they're asking for is how much heat is put in, and that's exactly what QH is from our diagram. So we're going to get from that QH is equal to 25 times 10 to the third divided by 0.18. So 25 times 10 to the third divided by 0.18, and that gives me 1.39, one extra sig fig there, times 10 to the fifth joules. So that's the actual heat that we put in. Notice we're only getting 25 times 10 to the third joules out, but we're putting in uh, basically 139 times 10 to the third joules. So it's 139 versus 25, not very high. Now for part B, and this was part A, by the way. Now for part B, it says how much heat is discharged as waste. Well, that means QH, right? Because our diagram clearly shows that QH is coming in and QL is what's going out. I hope I said QL. I don't know if I did now. I come think of it, but for some reason my brain just started thinking that I might have said QL, H by accident. But we've got QH. We've got W. Now we want QL because the question's asking for the heat that is discharged as waste. So what we do know is that QH is also equal to W plus QL. So that means QL has got to equal QH minus W. And that is 1.39 times 10 to the fifth joules minus 25 times 10 to the third joules. And that gives us QL is equal to 1.14, one extra sig fig again, times 10 to the fifth joules again each second. So what we found was the total heat put in was 1.4 times 10 to the fifth joules. The heat wasted was 1.1 times 10 to the fifth joules, and the amount of work that we got out was just a mere 25 times 10 to the third joules. Any questions on that one? Okay. Some of you came in, but it looks like y'all might have already taken care of it. Thank you, Anahi. Uh, you looks like you might have already taken care of it. I just want to remind everybody to chat me your first and last name if you haven't done so already. All right, now you're going to see I'm deviating quite a bit from the order of the chapter 20. So you can still read chapter 20 as you should do, even though I'm not testing you on the entirety of it. It's definitely something that'll help you. And when you go into your, if you go into engineering, for instance, if that's your major or chemistry, you're going to cover stuff similar to this later on. And the more that you get from this instance of looking at our chapter 20, the more helpful it will be later. So by all means, try to get as much out of it as you can from the reading, but just know when the test time comes, I'm going to be a little lighter on you. So the homework's a really excellent measure of how good you're doing, even though it doesn't cover a lot of it doesn't cover the heat pumps and stuff like that. It still covers well, it does cover the heat pumps in terms of there's a tutorial in there for you to do it. So you'll still learn a little bit more, but when the test time comes, you'll have a lot simpler problem set to worry about. I've tried to cut them out of the practice test, but it still has a lot of questions that are otherwise related. If you run into those, don't even worry about it. You can skip right over them if it says anything about a heat pump. But if it does say something about a Carnot engine, if it says something about entropy, those things are fair game. All right, let's go on to the next section. So now, as I had warned, we're going on to talk more about this specific engine because it turns out when we're trying to generalize the second law of thermodynamics from just heat only spontaneously flows from a hot object to a cold object, uh, that is a very select set of processes that we can apply it to. For instance, in a heat engine where heat is transferred from one object to another, and then part of that heat is turned into work, and the rest of that heat is put out. That's not an easy thing to say heat flowing from a hot object to a cold object. There's a lot of processes going in there, so it's not obvious that it's easily applicable to a heat engine. But it turns out, ultimately, by studying the heat engine, we'll learn a more general form of this second law of thermodynamics, and therefore we're going to take the Carnot engine as our model engine, even though there's a lot of other ones too. But Sadie Carnot actually handled that specifically. He gives us a second law of thermodynamics that's true for all heat engines, not just his heat engine. So, the Carnot engine is a theoretical construct conceived by Sadie Carnot, and it helps science progress towards a better understanding of physics. The Carnot engine is an idealized engine with four steps. It starts off with an isothermal expansion at temperature TH, during which heat QH is put into the working substance. So when you have a heat engine, and your book takes the time to show you some heat engines. For instance, it talks about the four-stroke internal combustion engine, which is what modern day car engines are. It talks about reciprocating steam engine, and it talks about a steam turbine. The reciprocating steam engine, that's, a lot of people make those. For instance, when I was teaching a thermo class, or actually I was teaching a conceptual, more of a technical physics really, at a community college out in Sanford, North Carolina, I had a bunch of motorcycle guys that were taking this class because, they were studying to work on motorcycles. Harley Davidson even gave us like two two or three free Harley Davidsons every year, but we weren't allowed to ever drive them on the road. They could never be registered, but they gave them to us to just work on. And these students were, real gearheads. They love to make stuff. They love to build stuff. And one of my students made a reciprocating steam engine like immediately. Like he brought it into class with a little sterno can and that sort of thing. So I would say that that is a first start at trying to make an engine yourself would be a reciprocating engine, because what happens there is you have some kind of working substance, which in this case would be water. And in this case, he put a sterno can under it. Sterno is a little fuel that you can use when you're camping, and you light it. And basically what happens is the flames start to heat up the water inside of this little tank. That's basically the tank was literally a soup can, and he had built a little piston that was more or less a piece of leather riveted to the lid that he had cut down smaller. And what happened is, as the steam got really really hot, or as the water got really really hot, the steam started to build up enough pressure where it could push against that piston, and it would rise up like this. Well, he had a little bar that came from that little piston and went up to a more or less like a lever, and that lever would actually cause a axle to turn. So it would come up like this, and then when it got that high, there was a little hole in the side where the steam could be let out, and that steam would let out and cool down, and the momentum of the turn would actually cause the piston to go back down again, and the process would start all over. And he ended up making basically a little steam engine car. So it is kind of helpful, but you don't have all that because I'm just jumping right into this. What I will show you is that on a pressure versus volume diagram, oh, no, that's volume, sorry about that. On a pressure versus volume diagram, what we're looking at is an isothermal process, isothermal process right here. And this is the isotherm that it's riding on. That's at temperature TH, and that's from point A to point B. And you can see, because it went from A to B from left to right, that's an expansion. And then step two says an adiabatic expansion. So we go from B to C now. And the adiabatic expansion, during which the working substance cools from TH to TL. So now we have this isotherm, which is at temperature TL, like that. And draw the arrows to show which way we go. And then step three is an isothermal compression, which heat QL is released. I'm going to show that too in a second. So in this process, it goes right here, and that's to point D. And then step four is an adiabatic compression during an adiabatic compression that returns the engine to its initial state at temperature TH. So now it goes back up like this. So that's our Carnot cycle. And I should show that during this phase, an amount of heat QH is coming in. And during this phase, an amount of heat QL is leaving the system. So that's what the Carnot engine process looks like. But all of the processes are assumed to be reversible and infinitely slow. So reversible means that it's always just a hair off of equilibrium. So it's sort of seen as if we've got an equilibrium state and it jumps to another equilibrium state because it goes at such a small amount that it always sort of stays in equilibrium. And by doing that, we eliminate things like friction and stuff like that that could make an engine be less efficient. So, in that sense, Carnot's making an ideal engine. He's making an engine that we can never make, but is a theoretical construct that gives us sort of the best of the best. And you'll see that surprisingly, you can't get a very efficient engine from a heat engine, period. I mean, it's like, 50%. Wow, that's an amazingly efficient heat engine. But that's a Carnot engine. So imagine a Carnot engine at 50%. That means which you'll learn in a second, that means the actual efficiency of a real engine designed on that model wouldn't be anywhere near 50%. So that's the idea. The Carnot engine is an isothermal expansion at temperature TH during which a heat QH is put into the working substance. Step two is an adiabatic expansion during which the working substance cools from TH to TL. Step three is an isothermal compression during which heat QL is released. And step four is an adiabatic compression that returns the engine to its initial state at temperature TH. And because of all this, because it's cyclic, as we said, the total internal energy has to be zero because internal energy is a state variable. And if you return to the state, then the variable has the exact same value that it had before. Okay, that's the nature of what a state variable is. And remember, I explained to you, though I couldn't give you all the details that you wanted, state variables are the things that we can put D's in front of. Like you can put a D E internal, meaning a differential E internal, because E internal is a state variable. We couldn't put a regular D in front of Q or a regular D in front of W because they're not state variables. Uh, then, of course, the very next step, we put a D in front of a Q and a D in front of a W. But again, that's more of us. We have to sort of imagine something's going on there that we just can't tell you about right now. Just know that it's partly to do with those differentials and how I think in your differential equation class you'll learn about exact differential equations, and exact differential equations can be written in the form of df is equal to the partial derivative of f. I know this is some language that many of you haven't covered because the partial derivative doesn't come in until like the third semester of calculus, but it's a derivative of a function that has more than one variable, and you pretend like all the other variables when you're taking this derivative are just constants. So if you had a derivative of a function that is a function of x, y, and z, you could take a derivative of f, but just with respect to x, pretending like y and z are constants. If that was the case, then you'd be taking a partial derivative. So the df would be the partial of f with respect to x times dx plus the partial of f with respect to y times dy plus the partial of f with respect to z times dz. In your differential equation class, you're probably only going to have two of those terms, but that's the main thing. So if you can't write it like that, it's not exact and it's going to have some bearing on it being a state variable versus non-state variable. So don't feel bad if you don't understand it. I definitely did not understand it when I went through this, when I was taking this course, and I'm actually pretty rusty on it. So I have to go do a deep dive to explain it any better than that. So we'll just move on from there. Anybody have any questions other than that one? All right. So again, I'm telling you, I'm skipping the order that your book's going in because I'm trying to avoid a lot of the pains. What your book does at this point is, for starters, it immediately after introducing the Carnot engine, it starts working problems with the Carnot engine, but with the formula QL 1 minus QL over QH. Uh, but then it starts using the ideal gas law and some different things, and it does a lot of neat tricks. And next thing you know, it works out that the efficiency of the Carnot engine is not just 1 minus QL over QH, but 1 minus TL over TH. But there's a quick and dirty way you can do it, and that's what I'm trying to do here is just show you another way that also makes sense, but maybe even makes more sense because you don't have to do all that algebra. So, Carnot's theorem, all reversible engines operating between TH and TL have the same efficiency. Any irreversible engine operating between the same two fixed temperatures will have an efficiency less than this. So I just realized in this writing of this, I wrote Carnot's theorem, but I didn't mention that it is the second law of thermodynamics. All these things that I'm writing down as theorems and statements, those are all versions of the second law of thermodynamics. So that Carnot's theorem is another version of the second law of thermodynamics, or at least related to it. Kelvin Planck statement, no device is possible whose sole effect is to transform a given amount of heat completely into work. For that one, let me just draw a quick picture to help you understand what that means. So what he's imagining in the Kelvin Planck statement is a heat reservoir and then heat coming into it, QH at temperature TH, and then every bit of that going out as work. That is not possible. So that's what this Kelvin Planck statement is. No, there's no way you can make a machine that 100% turns heat QH into work W. There's always got to be some lost heat. So to move further, we need to introduce another state variable. The state variable is called entropy. You might have already heard of this. I hope you have. Perhaps you covered it a little bit in high school. Maybe were awesome enough that you got to take a physics class in high school, or maybe y'all even talked about it in chemistry or earth science or something like that. It's often called the disorder of a system. The entropy is called disorder, and that's a pretty good way of understanding it if you sort of really understand what disorder would mean. So, disorder sort of means that you have a lot of different ways that you can achieve the same goal. If there's only one or two ways that you can achieve a goal, then that's a low entropy state. Whereas if there's a billion ways, then that's a high entropy state. They often make statements like it's a lot easier to pull into a parking space than pull out of a parking space than it is to pull into a parking space. They occasionally people will state that as a version of the second law of thermodynamics, and in some sense it is because if you imagine a parking space, which I could draw, let me flip back a little bit, and I'm going to erase this a little later. If you imagine a parking space looks like this, and let's imagine that we're parking legally, not like some jerks park. Your car is obviously smaller than a parking space, or it wouldn't fit. So your car might be something more like this. Okay. Now notice there's a lot of different ways this car could fit in. I could shift it over 1 centimeter and then it would be in that spot. Another centimeter and it'd be in that spot. And another centimeter, it'd be in the next spot. So on and so forth. I could also slip it forward and I could slip it forward again and I could slip it forward again. All of those are validly parked cars. I could also slip it backwards. So in this case, it'd come up with all these. And I'm doing all these in addition to the things I already said. So I could also come over here, go to the right, 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 go to the right. That's some of the ways that I could park this car in there. And you see there's a lot of them. But I haven't even gotten to all of them because I could also park, crooked, cattywampus. But again, as long as the car is inside of the vehicle, there's still, or inside of the parking space, inside the lines, in other words, then it would still be a valid parking space. So you can see in parking a car, there is a lot of parking, a lot of ways you can park, and you'd think that that's a highly disordered state, and it seems to be compared to a much smaller parking space with a much bigger vehicle, but compare this to pulling out of the parking spot. If you wanted to pull the car out of the parking spot, it could be here. It could be here, 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 it could be. So you get like an infinity, in fact, of places where you could actually pull the car and be out of the parking space. So yes, there is some disorder, i.e., entropy of parking the car, but the entropy is way smaller in the parked car than it is in the unparked car because there's a lot more free ways you can be out of the parking space than there are free ways to be in the parking space. Do y'all sort of get that a little bit? Anybody have any questions about that? So it that seems really abstract. I know when my chemistry teacher back at College of the Albemarle told me this, I was a little skeptical. I thought he was sort of waving his hands and just keeping a secret, sort of like I was talking to you a second ago about the non-state variables not being able to put d's in front of them. I really felt like he was doing that. But then when I got to statistical mechanics, I found out exactly what it was, and I was like, oh well, it is almost exactly that. And you'll see that in the last section where they talk about the entropy being K times the ln of W. You might want to write that down somewhere. Entropy, I'll write it right here just so y'all remember to look it up. S equals K ln W. That's the sort of the final version of the second law of thermodynamics that this chapter covers. So this is what the entropy is. Entropy is a state variable S, and it's defined by delta S is equal to the heat added or taken away divided by the temperature at which that occurs. So that's why I wrote Q over T. Remember, Q is heat added. However, in this efficiency stuff, QH, QL, and W are all positive, but only in that section. Everywhere else, they've got the normal definitions that they had from our first law of thermodynamics. You can also write, instead of a delta S, you can actually write a DS, but then it has to be D bar QT, again, for that same reason. But you'll see even in the book, he's going to immediately write DQ and he's going to integrate it. And there's some validity to that. Just know that it is valid to do it the way it was done and everything, but it's kind of weird. So just again, don't ask me about that part. It's kind of a pain. So here's another general statement. So this one's yet another version of the second law of thermodynamics. The entropy of an isolated system never decreases. It either stays constant in reversible processes or increases. What that means is if you happen to have a reversible process, then the entropy stays the same. Q over T for the hot side, for instance, QH over TH will equal Q over T, QL over TL for the cold state. That's what happens. And because of that, I can immediately make a really quick shortcut instead of all the derivation that your textbook does. I can make a quick shortcut into the new version of Carnot's efficiency. So here's another equivalent statement. The total entropy of any system plus that of its environment increases as a result of any natural process. So writing that in equation form, it means the total change in entropy, delta S, is equal to delta S of the system plus delta S of the environment, and that's greater than zero. Okay. Now, this is the version, if you've ever heard someone say that, for instance, the theory of evolution is contradicted by the second law of thermodynamics, it's really not. Okay. And this is why it's not, because yes, we are taking a disordered collection of molecules and from it making a very ordered section. But that can happen, but it happens at the expense of the environment. So we can make the entropy of the system go down as long as the environment goes up by more than it goes down. So we can do that because the Earth has this ginormous sun over there that gives us heat Q at temperature T, so it can actually put in the necessary entropy that we need. So just keep that in mind if you ever hear that old saw. Okay. So now I'm going to go to showing you what the Carnot efficiency becomes. So the Carnot efficiency was 1 minus QL over QH, and I just said for reversible processes, QH over TH is equal to QL over TL. Now from this, I can solve this by multiplying, or let's say dividing both sides by 1 over QH. Actually, I should say multiplying each side by 1 over QH, like that. And I'm also, instead of just multiplying by 1 over QH, I'm going to multiply by TL over QH. And in so doing that, I'm going to get TL over TH is equal to QL over QH. So now you can see that the Carnot efficiency becomes 1 minus TL over TH. And my H fell in half there. So everybody see now the new version of efficiency for the Carnot engine? All right, so now we can start working examples. So here's example 20-2. Again, I'm pretty much sticking to the examples of the book, but I'm trying to write them in such a way that they hopefully don't violate copyright, and hopefully that works. I'm not trying to make Giancolli mad. I'm a big fan, that sort of thing. So a steam engine operates between 530 degrees Celsius and 285 degrees Celsius. What is its maximum efficiency? So this is a steam engine, and what we know from the versions of the second law of thermodynamics that we heard is that all steam engines are less efficient than the Carnot efficiency. So if we calculate the Carnot efficiency, then that's the maximum efficiency it could ever reach, and it's not even going to get that. Okay, so that's what's going on here. So in this case, we've got the operating temperature of 530 degrees Celsius and 285 degrees Celsius. So solution, we know efficiency is equal to what you get divided by what you pay for, which also turns out to be 1 minus QL over QH, which we just showed for the Carnot engine becomes E Carnot is equal to 1 minus TL over TH, like that. So what we can see here is TL is 285 degrees Celsius, but we got to remember that this is since the units of entropy, which I showed you a second ago, entropy had a value of Q over T. So that means the units of entropy are the units of Q divided by the units of T, and of course the only acceptable unit of T is the Kelvin, so this becomes joules per Kelvin, and that means we cannot use temperature in degrees Celsius, we have to use Kelvin, so TL is actually going to become 285 degrees Celsius plus 273, and that'll give us Kelvin. So if I add 285 and 273, that gives me 558. And remember, we don't write degrees with Kelvin. TH is supposed to be 530 degrees Celsius. So that's going to mean TH is equal to 530 plus 273. 530 plus 273 gives me 803 Kelvin. Therefore, the efficiency of this is 1 minus 558 over 803. And of course, the efficiency is a pure number. I'm going to do 558 divided by 803. That gives me 0.69. I got to subtract that from 1. So that gives me 0.305, and I'll give it one extra digit. 51 is the efficiency, which is on the order of 30.5%. So that's the efficiency. Any questions on that one? All right. Now, here's another example. This one I'm going to have to go with the book just because I didn't have enough time to write all these down. I was trying to do all this stuff while being sick and all that good stuff, so it didn't work out too well. But it says example 20-3, a phony claim. So actually, I think I'm going to start this on another page. And it says a engine manufacturer makes the following claims. An engine's heat input per second is 9 kilojoules. Q input, so that's QH, is equal to 9.0 kilojoules at 435K. The heat output per second is 4 kilojoules at 285K. So QL is 4.0 kilojoules, and that is at 285 Kelvin. Do you believe these claims? Okay, so what we have here is two sets of data really for us to calculate the efficiency. We can calculate the efficiency of an engine in general as W over QH, which remember turned out to be 1 minus QL over QH. And then we have the way of calculating the Carnot efficiency. And if we ever found that a person is claiming an efficiency equal to that of Carnot, we know they're lying. Uh, until we, definitively see some series of experiments that everybody in the world can repeat and get the same response, because that's what it would really take to overthrow something as big as the second law of thermodynamics, is that everyone be able to regenerate the same experiment. So what we're going to do is calculate the efficiency according to the heat, and then we're going to calculate the efficiency for a Carnot engine operating at those temperatures and see how they compare. So here's the efficiency equals 1 minus QL over QH, which is 1 minus 4.0 kilojoules over 9.0 kilojoules. Now, 4 ninths is 0.44444, so 1 minus 0.44444 should be 55555. So 0.555 is the efficiency of the engine. So he's claiming the efficiency is around 55.5%. Now, the efficiency of the Carnot engine operating between these temperatures is 1 minus TL over TH, and that's going to give us 1 minus. Now, in this case, we're going to do 285 over 435. So 1 minus parentheses 285 divided by 435 in parentheses gives me 0.345 roughly. So the Carnot efficiency operating between these temperatures is only 34.5%, whereas he's claiming an efficiency of 55.5%. So I would not invest in his company, and he's probably a charlatan, or he's a goober that doesn't understand physics well enough to realize that he's screwing up. Any questions on that? So you can be Fox Mulder all you want. You want to believe, but don't. I know that's a really old reference. That's like 1990s television. So, anybody have any questions? All right. So your book then goes after it does this example 20-3. That's when it gives you that Kelvin Planck statement: no device is possible whose sole effect is to transform a given amount of heat completely into work. That's when they do that. And then they show a diagram just like mine. Then they go over the Otto cycle, uh, which is made up a little bit differently than the Carnot cycle. The the Otto cycle appears to be an adiabatic process followed by a isovolumetric process, followed by another adiabatic process, followed by a final isovolumetric process. So that's the difference in them. And you can ultimately do the same sort of derivation that he did for the Carnot engine with that one. He then goes into refrigerators, air conditioners, and heat pumps. What you need to understand is that, and I'm just going to briefly talk about this, the whole idea of a refrigerator or an air conditioner is you're taking heat from a cold thing inside the refrigerator. For instance, like don't think about it when you first bought the refrigerator. Think about the refrigerator as it is like right now. The refrigerator, if you open it up, it's probably 37, 38 degrees Fahrenheit inside, and the kitchen that it's in, assuming your kitchen, your refrigerator's in the kitchen. Sorry, that's a story a friend of mine told me about living in the country. I might brief you with that sometime later. But anyways, in the kitchen, it's around 70 degrees, say. So you got 38 inside, you got 70 on the outside, and you're literally trying to pull heat from that 38 degrees and put it into that 70 degrees. You might not want to heat up your kitchen, but that you don't have any choice on that. That's what the refrigerator is going to do. But that's what it is. Notice that's exactly the opposite of what heat wants to do, but you're not doing it spontaneously. So you're not violating the second law of thermodynamics. And you can tell because the power company is going to charge you for every bit of that refrigerator being plugged in. So what's being done is you're actually taking the heat out of the cold reservoir inside of the freezer compartment and the refrigerator compartment, and you're dumping it out to the outside air. So it turns out that it's sort of like a heat engine running backwards. So instead of work being put out, it's actually work going in and cold heat from the cold reservoir coming in. So you got QL coming in, you got work coming in, and then out comes QH into the hot reservoir. So it's sort of a backwards thing. Let me show you what I mean by that. So in terms of our heat engine diagram that I showed you before, it looks like this, only now in this scenario, it's work coming in, it's Q low from T low coming in, and it's QH going into TH. That's what a refrigerator or air conditioner does. Okay, so that's the big thing here. You can see it sort of acts like a heat engine because the heat engine had all these arrows backwards, right, compared to this. So that's what it does. And in principle, if you've ever looked at a refrigerator, basically it has a working substance which used to be Freon, but we had to get rid of that because of the ozone and all that good stuff, which really was a problem, trust me. Uh, but we had to get rid of all that, and we're now using something similar, but it's just not the same stuff. Now, the thing is, you can take that stuff and compress it, and it'll get really, really hot, like everything does. Like if you, for instance, if you let the air or let the spray out of a spray can, like a hairspray can, which obviously I use a lot, you notice that the hairspray, when it comes out, it's actually cold. The reason why is it went from high pressure to low pressure. If you force something to go from low pressure to high pressure, it gets hot. If you force something to go from high pressure to low pressure, it cools off. So if you take this compressor and compress this fluid, this working substance, and then you run that fluid through there, then it can actually be used by expanding it. You run it through the compressor, and then you take the compressor and let it expand it. By expanding it, it makes it really, really cold. Now, if you allow the air that is in the refrigerator compartment to hit that cold pipe with the cold freon in it, then that cold pipe is going to steal the heat from the air in the refrigerator and freezer area, and then they'll recompress it, make it hot again, and then decompress it, make it cold again, and come back out. That's pretty much how the refrigerator works. So that's why you have a compressor and condenser and stuff like that in it. And when you go to do the efficiency of it, they do something other than efficiency. It's called the coefficient of performance, the COP, and it is, as always, what you get divided by what you pay for. And what you get is the amount of heat QL that you're pulling out of uh, the cold area, the refrigerator and the freezer area, and what you pay for is the work you put in. So in this case, you can see that QL plus QW, or excuse me, QL plus W is equal to QH. And because of that, you can replace the W with QH minus QL, and we get the coefficient of performance is equal to QL over QH minus QL, like that. So I think that's good enough for you to follow what's going on with it. It even talks about the SEER rating, SEER, so that's kind of stuff that you want to know if you're ever planning on owning your own home. Not a whole lot, but you need to have some understanding of it, just to make your way around salespeople that try to not be as honest as they like as you'd like them to be. Okay, so I'm going to skip on these examples because I'm not going to require you to do them anyways, and we're going to move on from that to entropy. So let's look at an entropy example, and I'm not going to do many. I'm just trying to give you an idea. So an ice cube of mass 56 grams. This is example 27. So we have an ice cube of mass 56 grams is taken from a storage compartment at 0 degrees Celsius and placed in a paper cup. After a few minutes, exactly half of the mass of the ice cube is melted, becoming water at 0 degrees Celsius. Find the change in entropy of the 56 grams of ice water. Okay, so what we have here is a mass equal to 56 grams, which equals 0.056 kilograms, just in case we need it. I think I'm going to end up using grams anyway, so it won't matter. And it goes to, after a few minutes, exactly half of the mass. So it goes to, uh, what, 25 plus 3 would be 28, 28 grams of H2O liquid plus 28 grams of H2O solid, something like that. And they want to know the change in entropy. That's the question. Okay. Well, we know solution. We know delta S is equal to the heat divided by the temperature. Now, the heat added would be a positive quantity, heat taken out would be a negative quantity, that sort of thing. So what we're looking for here is just a magnitude right now. We're just trying to find the change in entropy. What we do know, for instance, is the latent heat of vaporization, or excuse me, the latent heat of fusion for ice. Ooh, I think it's 79.7. So I'm going to go ahead and write that down too. So L sub F is equal to 79.7, and that turns out to be grams, or excuse me, that turns out to be calories per gram. And probably I do need to do it in joules, so I guess it'd be worthwhile to go ahead and say, oh yeah, the value is 333 kilojoules per kilogram. So that's the heat of fusion there. Okay. So the heat required to melt the ice, Q, would be equal to M times L. And in this case, we're only melting half of it. So it's going to be 0.028 kilograms times 333 kilojoules per kilogram. And that gives me 0.028 times 333 gives me 9.324 kilojoules. Now notice I've given it two extra digits beyond sig figs, and that's okay. We do know the temperature took place at 0 Celsius degrees, so we need to convert that, of course, to Kelvin, which would be 273. So we get that delta S should be Q over T, which should be 9.324 times 10 to the third joules, because it's kilojoules. And remember, these two are not sig figs. And then that's going to be divided by 273 Kelvin. So I divide that by 273, and that gives me 34.2 joules per Kelvin. So that's the change in entropy. Now, the big deal here is what they're asking the change in entropy of the water is. So heat was actually, if you're melting it, heat came in to the actual ice cube. So that was a positive heat, and therefore the temperature was 273. So this is a change in entropy of positive 34. The fact that it's positive says that this naturally occurs, and of course it does. If you put an ice cube in a cup, it's going to melt. Any questions on that? Your book then goes on after that example, and it proves that entropy is a state variable. That's a very interesting thing. That's the like sort of the first step of you trying to understand the difference between the state variable and other variables. So if you can read that, you might get a little bit more insight into it. And to be honest with you, I didn't reread it this time. That's why I'm not necessarily that well prepared to answer questions about the D bars versus the regular Ds, other than my knowledge of the mathematics of differential equations. So, any questions on that before I move on? Okay, I think I'm gonna not do this one. I was looking at example 20-8. That's a reasonable example, but I really just want to get finished with this chapter. So I'll say look at example 20-8. Uh, it is fair game, but I want to get on a little bit further than that. So, and 20-9. The 20-9 is really just a neat little exercise where you're learning about free expansion, and it's kind of interesting. I doubt I'd ever ask you anything about that, but I would like you to look at it, so that's why I put that there. There's some other examples it does, 20-10, so on and so forth. But what I'm trying to get to, it also talks about times arrow, which is kind of neat, order to disorder, which is kind of neat. But the big thing that they're talking about, again, the biological development that I was telling you, that's in the section as well. The unavailability of energy and the heat death of the universe, that's another thing. Here's another version of the second law of thermodynamics that I didn't even realize they must have put this in this fifth edition. I just started using the fifth edition last year, so I hadn't even didn't even notice it. But in any natural process, some energy becomes unavailable to do useful work. That's pretty much where I told you heat becomes energy becomes bastardized when it's in heat form. And yeah, they're talking almost in the exact same wording. They said degraded. So what it talks about then is in section 20-9 is the statistical interpretation of entropy in the second law. And in that, let me just pull up this. I'm going to stop sharing my screen, my iPad screen, and I'm going to go to sharing my textbook screen so you can get a feel for what I'm talking about here. So right here, they show something that's very instructive. It teaches us the difference between macro states and micro states. So it's talking here, you got four heads. This is basically tossing a coin four times in a row. So when you toss a coin, you can get a head or a tail. If you do it four times in a row, you could get a head, a head, a head, a head, and then you sort of treat these like an odometer. So you realize that you've got four slots because each of those is a coin flip, and each slot can be a H or a T. And you can sort of picture the H as like a one and the T is like a zero or something like that if you wanted. And then if you look at those four slots like an odometer that only goes from zero to one, then what you'd see is the far right odometer goes from, first off, all of them being zero to the far right odometer going from zero to one. Now, once that far right odometer reaches one, it has to go to zero again, but that causes the one to the left of it to go up to one. And once that one goes up to one, the next place it goes to zero again, and that makes the next one go to one. So that's what you're seeing right here. It's T on the rightmost one, then T on the next to the right, then T on the next to the next to the right, and T on the leftmost one. And then two heads and two tails. The way you can get that is starting with two heads on the right. And again, we're just doing sort of the odometer thing. But ultimately, what you see is there's only one way that you can pull off four heads. There are four ways that you can pull off three heads and one tail. There's six ways you can pull off four heads and or excuse me, two heads and two tails. There's four ways you can pull off one head and three tails, and there's one way you can pull off all tails. So that's a key to understanding the statistics that we're getting ready to talk about. So if we look a little further, you can imagine, let's say we throw uh, a coin 100 times, and then you try to make that same sort of table. You can get 100 heads and zero tails exactly one way. Okay, just like you could only get four heads one way. You can also get zero heads and one tail exactly one way as well. Or excuse me, zero heads and 100 tails exactly one way as well. Now, when you look at this, you'd have to count all these individual states, and you can see that all these individual states, the macro state being, what is the orientation of the head of the coins at each state from either a head or a tail, and the micro state is the number of ways you can do it, and then the probability is found by taking this number, dividing it by the total number of microstates. With that, and again, this I'm not really explaining it all that much, but the key thing is it turns out that entropy can be defined as S is equal to K times the ln of W, where W is called the thermodynamic probability or sometimes the disorder probability or parameter. This W is proportional to the probability of occurrence of that state. So the W is well, let's look at this example, for instance. Maybe that'll help you better understand it. So it says free expansion statistical determination of entropy. Use equation 20-14, which is that one right there, to determine the change in entropy for the adiabatic free expansion of a gas, a calculation we did macroscopically in example 20-9. This is why I was telling you you do want to do example 20-9 as well. Assume W, the number of microstates for each macro state, is the number of possible positions. We assume the number of moles is N equals 1, and then the number of molecules is N, big N, which is equal to N times Avogadro's number. We let the volume double, just as in example 20-9, because the volume doubles, the number of possible positions of each molecule doubles. And from that, when the volume doubles, each molecule has two times as many positions, microstates, available. For two molecules, the number of total microstates increases by 2 times 2, or 2 squared. For Na molecules, the total number of microstates increases by a factor of 2 times 2 times 2 times 2, where you have N sub A, meaning Avogadro's number of 2. So that's 2 to the Avogadro's number. That is the probability of the number of microstates in version 2 when it's twice the volume divided by the number of microstates when it's the single amount of volume is 2 to the Na power. So if you calculate the entropy for that, the change in entropy would be S2 minus S1, which would be K ln W2 minus K ln W1. And remember, the difference of logs is equal to the log of the quotient of the two. So it's going to become W2 over W1, which lo and behold was 2 to the Avogadro's number. when you take the natural log of something raised to a power, the power just comes out in front of the natural log. So you get K times Avogadro's number times the ln of 2. And of course, K times Avogadro's number is just R, and then you get R times the ln of 2, which is exactly the same result they got in example 20-9. So I'm not going to make you do those kinds of calculations. I just wanted you to know uh, that this has something to do with sort of like those parking spaces, the number of ways you could fit in a parking space versus the number of ways you can fit out of a parking space. So don't worry too much about the mathematics here. You'll see that I don't ask you too much about that. And I'm going to double check on my uh, practice test, which I've already made practice test 2 available because it's supposed to be due for you guys on the 16th, I think it is. So make sure you get your online test 2 done by the 16th, and the practice test has that already. I haven't posted the online test yet, but if you're ready to take it and you want it to open up, just let me know. I'll go ahead and open up early. Otherwise, I tend to give you about a week, so that should be, I think, this Saturday or Sunday, maybe Monday. I should open it up. If you want to do it before then, just give me a holler, or if you see that I forget, give me a holler. Anybody have any questions? All right, well, that's all I really wanted you guys to be able to pull off for this chapter 20. So I'm going to try to be really easy on you. If I give you a test and it looks like uh, y'all didn't get the chapter 20 part very well, then I'll have to regroup and probably give you some more points or figure out some way to curve it because I'm not trying to brutalize you with this chapter 20. I just wanted you to know some of the fundamentals of it. So I don't think it's unreasonable for me to ask you how to solve efficiency problems with Carnot engines and regular engines. I don't think it's unreasonable for me to expect you to memorize the versions of the second law of thermodynamics, and I don't think it's unreasonable for you to know that it has entropy in it and that has something to do with disorder and like the number of parking spaces and the formula K ln W, even if I don't even get you to actually use the equation, but possibly state it. So you're all free to go. Thank you for coming, and just make sure you chat me your first and last name if you haven't already. But have a good weekend, stay safe, and let me know what I can do for you. Thank you, Mouse.
Mr. Younger, I had a quick question about the environmental statement that you stated. I'm still a little confused on that.
Which statement was it?
The environmental statement.
Oh, okay, gotcha. So there's a quantity called entropy that's given by the change in entropy is equal to Q over T. What I was saying with that is the total entropy is the entropy of your system plus its environment. There are, closed systems that we could imagine, in which case that first delta S is the only one that's non-zero. But in general, systems have environments as well as the system itself. And if you take into account the change in entropy of the system plus the change in entropy of the environment, that is always going to be, if it's a perfectly reversible process, zero, but which is never happening. But if it's not reversible, it's going to always be greater than zero.
Okay. Cool. Thank you so much.
No problem. Hopefully that cleared it up.
Yeah, I believe so. Yeah, I'm just trying to think of applications for that, but I
Yeah,
think I
it's
am.
more like if your system was a spoon and you stuck it inside of a cup of water, if you calculate the change in entropy of the spoon, you would get basically, if the water was hotter, for instance, you would get that the change in entropy for the spoon would be a positive quantity because the heat was actually added at some, average temperature or something like that. But if you calculated the entropy for the whole system, which would include the loss of heat from the water and the temperature that the water was at, you'd find that the total entropy in that case would be greater than zero, even though the entropy of the spoon by itself was negative, or excuse me, was negative.
Okay, cool. Thank you so
Just because
much.
remember it's Q up
Yeah,
top and Q is negative if
right.
it loses heat.
Yeah, that's exothermic, right?
Exactly.
Oh, yeah. And what was it? Is it chapter 19 and chapter 20 practice test?
Hmm.
That's one. Okay.
Yeah, that one I opened up. I think I opened it up yesterday.
Great. Yeah, we'll definitely have to take a look at that.
Actually, I think your class might have all of them open already, but I did all the other classes last night.
Okay. Oh, wait, there's different online classes?
No, you all taking the same material and the same text, so I use the same practice test for it. I don't necessarily use the same test, but sometimes I even do that.
Okay. Okay, that makes sense. All right. Well, I'll be seeing you Tuesday.
All right, thanks, Alex. Have a good one, everybody.